Good day. How are you? My name is Senator. Senator is my nickname, but I'm Mr. Blessing. Blessing is my real name. So today, we're still going to cover up the application of Newton's laws. Since from the previous lesson, we discussed about the types of forces and how to draw the free body diagram, then how to draw the body diagrams. So today we're going to continue with the application of Newton's laws. As we are going today, we're going to start with the Newton's first law. So okay, so I'm going to open the examination guideline for grade 12, so that we can find out the Newton first law of motion. Yeah, so I'm not going to try the definition. Definition is already given in the examination guideline, but what I will do, I'll just try to explain the definition. So here to examination guideline, it's having your definition there. Okay, as you can see, it's the Newton first, second, and third laws of motion. Let's start with the Newton first law of motion. It says a body will remain in its state of rest or of motion at constant velocity unless a non-zero resultant or a net force acts on it. So here I'm going to try to explain this definition. As you can see from the definition, this Newton first law, it only applies to an object which is at rest, or it also applies to an object which is at motion with constant velocity. I hope you remember what is a constant velocity. Yeah, so it's either here the object is at rest, like this. I can give an example, like a book which is on the table. Let's say it's on the table here. There's a book here which is on the table, which is at rest. Okay, sorry, I'm not good in drawings. Okay, so let me try to draw the book here. Yeah, let's assume that this one is at rest. That is the book. Yeah, so Newton's first law says that from the definition, it says a body will remain in its state of rest. Yeah, which is there. I give you this scenario. It's a book which is on the table, which is at rest. Or if it's moving, it can be like, for example, there's a car which is moving here. Okay, given a car. If it is moving, this car which is in motion, I can give an example. It's moving with a constant. It must move with a constant velocity. So if you say constant velocity, which means the speed of the car or the velocity of the car must be the same. If this car is moving with, for example, let's say this car is moving with a speed or with a velocity of 20 meters per second, therefore this car must remain moving with the speed of 20 meters per second. So it means it's moving with the constant velocity. So whenever it's moving with the constant velocity, what you must know, which is very important, is that the speed or the velocity is not changing. It remains the same. So that is a Newton first law. Yeah. Then if we read the last part of the definition, they're saying okay, a body will remain, I'm starting again the definition. They're saying a body will remain in its state of rest or motion at constant velocity. Then they say unless a non-zero resultant or a net force acts on it. What does it mean if they say unless a non-zero resultant or a net force acts on it? It means that for here, for example, it's a non-zero resultant. I'm going to explain this part here. A non-zero resultant force. It can be resultant or net force here. It's fine. A non-zero resultant or net force, which means here if your net force, for example, F net, it's non-zero. For example, if you're saying it's non-zero, it can be usually more than zero, for example. So your net force here, if it's greater than zero, for example, I'll just give an example. But any number which is greater than zero, which means it's what? It's a non-zero. So at this scenario, you must know that whenever your net force is more than zero, it's no longer in equilibrium. So I'm going to explain what does this equilibrium means. There's what we call equilibrium. Yeah, when you're dealing with equilibrium, it is whereby if your forces are balanced, or if equilibrium only applies if your F net is equal to 0. I'm just going to give a simple example here. Let's say if an object is at equilibrium, I'll give an example here. Let's say a book which is on the table here. Yeah, as I said, let's assume that this one is at rest. If this book is at rest, we can consider forces. Let's say, let's try to draw the free body diagram. We did the free body diagram from the previous video. To draw a free body diagram, over say I'm going to have what? I'm going to have my there is weight, okay, moving down, and there's also what? Normal force. So since we are focusing with these vertical forces, we can say they are at equilibrium. If they're at equilibrium, which means they are balanced. This is what I'm trying to say. Which means the normal force is equal to the weight. Okay, sorry about that. Yeah, I'm saying normal force is equal to the weight. That is the meaning of equilibrium forces. The forces are balanced. So in other way, I'm trying to say the upward force is equal to the downward force. At the end, you are going to see that here, if I want to equate this equation to 0, I say normal force is equal to weight. If I want to equate this equation here, I need to equate this equation to 0. I will do like this, which means I can say normal force here. Let me use the red color here. Normal force minus. Okay, sorry about that. Let me use the. Let me try to show it here on the left side. I can say from here, from this part here. Yeah, since I said normal force is equal to weight, so if I want to equate this equation to 0, I can say normal force minus W is equal to, since I shift my W to the left, it will become negative. So you see now, guys, it will be normal force minus what? Minus W, normal force minus weight is equal to 0, which means your F net here is 0. So as I said, whenever your F net is 0, it's at equilibrium. So which means if it's at equilibrium, we are applying Newton's first law. But here you see the definition, they're saying unless a non-zero acts on it. So whenever your F net is not equal to 0, therefore your object is no longer at equilibrium. This is what I said here. Whenever your F net is greater than 0, or it can be F net less than 0, it's fine. It's also non-zero, that one, which means here this state here, we can say it's not at equilibrium here. This one here, it's not at equilibrium. So that's the thing that you must know, guys. At equilibrium, F net is equal to 0. If your object is not at equilibrium, F net is greater than 0, or F net is less than 0, which means your F net is non-zero. So that is the thing. So whenever the Newton first law only applies to stationary object, it only applies to objects which are at rest. It only applies to a motion at constant velocity, which means it also applies to only equilibrium forces. Yeah, this is where we apply our Newton first law. I hope guys you did understand this. If you cannot understand, try to rewind the video, then take your time, listen on what I'm trying to explain here so that you can understand the concept. Yeah, so from here, from Newton's first law, then we can go to Newton. Oh, sorry. Let's try to read down. Let's read our examination guideline to see what is the next step here. They're saying after the definition, we go to the second. Let's go to the second point. They're saying discuss why it is important to wear seat belts using Newton's first law of motion. I hope guys you know a seat belt you get it from the car. That seat belt, they try to keep us intact. They try to keep us at rest, or they try to keep us stationary, so that if maybe sometimes a driver can apply some emergent brakes, they will keep us not to move forward or not to hit on the dashboard of the car. So that is the use of a seatbelt. Its application of Newton first law of motion. But as time goes on, we are going to discuss more about this. We are going to use calculations. The time will be using the application of the formula for Newton's first law, and also some concept that we are going to do as time goes on. I'm having some questions here that we are going to do, that we are going to try to answer. Okay, that is it. So that point, there is state Newton's second law of motion. We go to Newton's second law of motion. I'm going to read it. It says when a net force acts on an object, the object will accelerate in the direction of the force. Okay, that force, remember, it must be net force, and the acceleration is directly proportional to the force. That force, it must also be the net force and inversely proportional to the mass of the object. Yeah, so this definition here for Newton's second law, it is whereby the motion, it's accelerating. Yeah. So now the motion here is no longer moving at constant velocity, as we discussed from Newton's first law. From Newton's first law, we agree that the motion must be at constant velocity. But for Newton's second law, here the motion must not be at constant velocity, which means the speed of the object must change, or the velocity of the car, it can be any object which is moving, the velocity must change. So it's no longer constant. There, whenever there's a change in velocity, we call its acceleration. It's accelerating. We are accelerating an object. So acceleration. So before I explain more of this definition, we are going to Newton what? It's Newton's second law of motion. Good. Yeah, from here. So if you check from this definition, it's Newton's second law of motion. They're saying when, let's read again definition. Yeah, they're saying when a net force acts on an object. So net force must act on an object, the object will accelerate. So whenever a net force acts on an object, the object will accelerate. What is to accelerate? That first thing that you must also try to cover. What is acceleration? What you must know, acceleration here is the rate of change of velocity. Yeah, generally the formula for acceleration is the change in velocity over change, sorry about this, it's change in velocity over change in time. That is the formula for acceleration. So what you must know here, acceleration only takes place when there's a change in velocity. For example, a car will start moving with what? With 10 meters per second. Then the driver will press the accelerator. Then the velocity will increase to, let's say, 20 meters per second. Now you see, whenever there's that change in speed, whenever there's that change of velocity, we call it acceleration. And remember, time will be taken whenever the car is moving from point A up to point B. Sometimes you can decrease the speed. Yeah, it's fine. Whenever you're decreasing the speed, still there's a change in velocity. There's a change in speed. For example, a car will be moving with 50 meters per second. Then a driver notice maybe an animal in the road, apply some brakes. So when you apply some brakes, remember the car will change the velocity from 50 meters per second to, for example, we can say 5 meters per second. So remember what is happening here. There's a change in the speed which is decreasing. So there's a special term which is given to that type of acceleration. The call it is what is deceleration. Deceleration, which means there's a negative acceleration, but we are going to do more of this when we do the calculation. It's very important whenever we are talking about acceleration. There must be a change of velocity. So your velocity can either increases or the velocity can decrease. That is it. So here from definition they're saying when a net force acts on an object, the object will accelerate in the direction of the force. So remember, your net force and acceleration, they must be in the same direction, like what is saying from the definition. So if your acceleration is acting to the right, even your net force must also act to the right. So their direction must correspond. Yeah. So now they say an acceleration is directly proportional to the force. So here they're trying to say if we increase the net force, the acceleration also increases. If you decrease the net force, acceleration also decreases. So they are inversely, they are directly proportional. Acceleration and the net force directly proportional. And the last term they say and inversely proportional to the mass. Yeah, which means they say acceleration and mass, they are inversely proportional. I remember that someone who's having a big mass, someone who's having a big body is having more mass. So it's not easy for that person to accelerate. It's not easy to push that person because he's having more mass. So remember, someone who's having more mass, more weight, the acceleration will also decrease, because it's not easy to push to push that person who's having a big mass, or it's not easy for that person to accelerate because he's having more mass as compared to someone who's having a low mass, very small mass, someone who's slender. Like it's very easy when you push someone who's slender, it's very easy to push her or to push him because the mass is very low. So someone who's having small mass, the acceleration will also increases. Yeah, so that is the thing which is happening. So this thing is even applicable in real life. Yeah, so that is where you see we go to the formula. The formula for Newton second law here, it says F net is equal to mass times acceleration. So you need to know that this one is it's your net force, or they call it a resultant. This is your resultant, or or a net force. Remember, it's measured in measured in newtons. So newtons is the SI unit of force, yeah, which is a net force. You can write it as capital letter N. That is the same. Then remember M is the mass of the object. Yeah, remember the mass is measured in kg. Yeah. Then A, we say A is it's acceleration. Remember, acceleration, it's measured in you must know the SI unit of acceleration. It's meters per second squared. So that is it. So that's one you need to know to apply this formula. It's very important. So I'm going to explain more about this formula. Remember, F net is equals to mass times acceleration. So from the Newton first law, they say F net is directly proportional to acceleration. So that is the so which means if F net increases, acceleration will also increases. Then we did talk about what they compare the mass and acceleration. So here to compare mass and acceleration, I will let me try to make acceleration the subject of the formula. Remember, acceleration will be equal to, if you make acceleration, it will be F net over mass. So if you check from this formula here, if I make the subject of the formula, you see that A is inversely proportional to the mass. So if acceleration increases, the mass will decrease. So that is that you must know. Okay, sorry about this thing I said here. Okay, it will be okay. So A here, we're gonna say A is okay. Okay, acceleration is directly proportional to 1 over m, like all of it. We're gonna say A is directly proportional to 1 over mass, but acceleration is inversely proportional to mass, which means if you increase acceleration, the mass will what? Will decrease, which means they oppose each other, as it is stated from what? From the definition. So that is it. So you must know, we are going to make use of this formula. It's very important. You must know how to apply it. Yeah. So that is it here. The next, we can go, let's move on. After that, after knowing how to define Newton's second law, you need to know how to draw force diagrams and free body diagrams for objects that are in equilibrium or accelerating. Yeah, I did explain this thing. We did the free body diagrams and force diagrams from the previous video. If you're not sure, you can go and check it out, but we're still going to apply it. Remember, we can use, usually when I do the calculations, we must make use of free body diagrams. So we're still going to do it now, because it's very important how to draw a free body diagram, because free body diagrams, they help us to find out the to calculate our F net. Okay, so for example here, then draw force diagrams and free body diagrams for objects that are in equilibrium. Yeah, as I explained, equilibrium, these are balanced forces. Equilibrium, it is whereby F net is equal to 0, or you must not draw free body diagram for accelerating object. So whenever object is accelerating, which means it's no longer at equilibrium, as I stated this one. I think I'm going to explain more of this. Whenever the object is not at equilibrium, we can say it's now accelerating. Yeah, that is the thing. F net is no longer 0. Yeah, we no longer have imbalanced forces. So here you see the next point here, they're saying apply Newton's laws to apply Newton's laws to a variety of equilibrium and non-equilibrium problems, including a single object moving on a horizontal plane with or without friction, moving on an inclined plane with and without friction, moving in the vertical plane, lifts, rockets, etc. Then two board systems joined by a light inextendable string by applying Newton's laws of motion separately to each of the bodies. Okay, both on a flat horizontal plane with and without friction, one on horizontal plane with and without friction, and the second hanging vertically from string over a frictionless pulley. Okay, it's fine. So we're going to do this thing. These are the calculations, these different scenarios that you need to know how to apply what your Newton's second law of motion formula. Okay, then let's go to, before we do the calculations, let's try to also to cover what the definition of Newton's third law of motion. I'm going to read it here. They are saying when Newton, you are now doing Newton third law of motion. When object A exerts a force on object B simultaneously exert an oppositely directed force of equal magnitude on object A. So you must know to what you need to know how to apply. Okay, you must know the application of what of this formula. Okay, it's very important. Remember here they're saying, I can give an example here from, okay, let me try to decrease my, it's fine here. Okay, here you remember that for this Newton, the state Newton's that law of motion, they say when object A, we can say this one is object A here. Yeah, when object A exert a force, yeah, this is object A exert a force here. Remember, let's say this one is the object, your wall here, let's say it's a wall. Yeah, so when object A exert a force on object B simultaneous at that same moment, it will also exert an oppositely directed force of equal magnitude. So for example, this B here, this wall will also exert same magnitude of force For example, here, let's say it's force A here, and here it's force B. So it will exert an oppositely directed force of equal magnitude, but on object A, but remember, they will be in different direction. So which means at the end, the force of A here will be equal to the force of B, but in different direction, remember. So we can say, since force is a vector quantity, we need to include direction. We can say to the right it's positive, then to the left it's what? It's negative. So we end up getting this expression here. Force of A is equal to the negative force of B, whereby that negative shows the direction of the force to the left, but force of A is to the right. So that is it. So you must know how to apply Newton. That law is like this. Then the next point, I say identify action, reaction pairs. So our action force here, it's force A. Then our reaction force here is what? It's force B. So that is it. Then list the properties of action and the reaction pairs. Yeah. So as you can see from these properties here, force B, it's only exerted. It's a reaction. It will be only exerted only if force A is applied. So that is it here. You can't have force B until there's what? Force A. So force A must be acted. Force A must be applied, then force B will be also released, but in same magnitude but different direction. So that is it about this Newton first law, Newton second law, and Newton third law. Okay, before we go to the last law here, let's try to do some calculation on the application of these formulas. So I'm having some questions here, simple questions, since I'm starting with the basics, the concept, so that the time we'll be doing complicated questions, you'll be having the good ground. So, or you'll be having the good foundation. So I'm going to, let's start to do